This is Phil Koperman, and I'll be talking about driver assistance versus automated vehicle safety. As an overview, first I'll talk about driver assistance, which is helping human drivers be better and safer, and then I'll contrast that with driver automation, in which the vehicle actually performs the full driving task, including safety. I'll compare and contrast safety argument implications as well as technology challenges. I'll start with an overview of automation modes for non-engineers. When talking about automation modes, and especially the role of human drivers in ensuring safe operation of vehicles, it's essential to have something that's clear, straightforward, and simple. This is a 4-row chart that shows 4 different modes that tries to make it very clear what the human driver role is in driving safety, and other safety. The first mode is the one that current drivers are generally familiar with, called Assistive operating mode. In this mode, the human role is traditional driving. The human takes care of driving safety as well as other safety. The next mode is Supervised mode. In this mode, the human's responsible not for driving. The car does the actual driving task, but the human driver is responsible for driving safety. And that means eyes on the road. The human's also responsible for other safety. Together, these 2 modes are driver assistance. An important line is crossed when entering automated mode. In automated mode, the human driver is allowed to take eyes off the road because the car is entirely responsible for both driving and driving safety. There still needs to be a human driver, but it's not really a driver so much as a captain of the ship. There needs to be a responsible person in charge of things that aren't driving but are safety related. For example, making sure the kids are buckled up in the back seat, and making sure that any cargo is both safe to transport and stowed correctly. Finally, in autonomous mode, there's no human with any responsible role for the operation of the vehicle, including the car does all the driving, the car is in charge of the driving safety, and the car is responsible for all other safety as well. Think about it. If you have an uncrewed delivery bot and there's nobody continuously watching every single second remotely, that means safety is all on the vehicle, and that would be autonomous mode. The important thing for this view of the modes is that driving safety depends on the human driver when there's a driver assistance set of modes, assistive and supervised. And driving safety depends on the car in automated driving modes, automated and autonomous. Let's go through the modes with some detail here. The point of assistive is to help the driver drive. The driver is responsible for steering, for speed control, everything you'd expect in a normal car. But a typical recent car will have quite a bit of assistance to help the driver drive better. Some of that assistance is better execution of driver commands. Anti-lock brakes help stop faster in bad conditions. Electronic stability control improves car handling. But those don't drive for the driver. Those just help the driver be a better driver. There are also some momentary interventions for safety. And the momentary is the important part here. This is not machinery taking control of the vehicle for a sustained period, but rather a momentary intervention to help the driver achieve safety goals that the driver should have been intending to achieve. For example, automated emergency braking can help the driver stop faster to avoid a collision when the driver was already intending to brake. More advanced versions might be more aggressive than that, but in general, the idea here is that the driver is still in charge of safety and that the vehicle is helping the driver accomplish obvious driver intent. There are some interventions to improve driver performance, but again, the driver is responsible for safety within an assistive system. Some standards that help with this are functional safety standards. ISO 26262 is the classic automotive one, and that helps make sure that even if there's an internal fault in the equipment, that the equipment still tries to execute driver intent to the best of its ability. Supervised driving is a system in which the driver monitors for safety, but the vehicle itself does the specific driving task. The vehicle does speed control, it does lane keeping, And the human driver remains responsible for safety. So in this picture, you can see this driver has hands off the steering wheel, and in some vehicles that's fine. But the driver is paying attention to the road and ready to grab the wheel as soon as it needs to be done. The point is, the car's actually doing the driving. The driver isn't steering. The driver's just being ready to jump in if something goes wrong. In particular, the driver can expect to have to intervene for edge cases, things that were gaps in the design or things the designers didn't even think of that will happen in the real world. So the role of the driver is to monitor and intervene. Now the vehicle has to get out of the way and let the driver start driving if the driver wants to, and the ISO 26262 functional safety standard will help with doing that. But beyond that, in any system like this, you're going to need some sort of driver monitoring. Human drivers have trouble paying attention for long stretches of automation running the driving task, and they develop a condition known as automation complacency, in which it's really hard to keep focused. So we're going to need some sort of driver monitoring to make this happen. Also, much more relevant here with supervised driving is safety of the intended function, SOTIF. ISO 21448 is the standard related to that. The idea here is that even if the car is operating perfectly, there may be gaps in its capabilities that it can't drive in some conditions, or a radar won't always see an object on every single pulse, and so on. Some of this happens a little bit with assistive, but in supervised driving, this becomes front and center because the car is responsible for tracking all the objects and getting it right all the time or almost all the time, so that the driver doesn't have to continually take over. With assistive and supervised driving modes, what you have is something that's helping the driver, and either the driver is driving in assistive or in supervised, the driver's supervising the driving, but is still ready to jump in. And in both cases, you have the vehicle reducing the workload on the driver to get the driving done, but the driver is still ultimately in charge. So you're hoping to reduce driver stress and reduce control mistakes. Active safety systems are a type of ADAS that helps in this regard. They can help avoid crashes by, for example, giving collision warnings and braking support to make sure you stop as fast as you can, as shown with this diagram. They're generally tuned to avoid false activations. The problem is that if you're driving down the highway and all of a sudden the car stops for no reason, somebody could get hurt, especially if you're being followed by a heavy truck that's not so quick on the brakes. And so a driver support system is typically designed so that it will intervene whenever it's sure it can intervene, but it will try and minimize false activations. Because after all, the driver should not have gotten into a situation where the support was needed, and the support is just helping out. It's not responsible for the safety. Because of that, arguably good enough active safety is good enough. And by that, what I mean is something very specific. It can't actively do something dangerous. So saying it's good enough because it only acts dangerously once in a while, that argument doesn't work. But what it can do is say, all right, I only activate when I'm sure I can help, and whenever I activate, I help in a constructive manner. That's great because the Advanced Driver Assistance System, ADAS, gets to claim credit for safety. It helped the human avoid a crash sometimes, but when it doesn't, it was the human's fault in the first place. So the ADAS system's trying to clean up the mess, and it gets to claim credit every time it does. But if there's a bad outcome and the ADAS couldn't prevent it, well, that's really the human driver's fault. The catch is you can't make unreasonable demands on human drivers. Humans have limitations, so you have to be careful with an ADAS system that you're not making it impossible for the human driver to actually be in control. If you decide the human driver is in control, you have to make sure the human driver really is in control. Consider, for example, an automated braking system that when you press the brake pedal, nothing happens because there's a defect in the system. That's going to be unsafe. So it's important the ADAS system only intervenes when it's constructive to safety to do so, and that it does not get in the way of the human driver trying to clean up a mess. A super important point here is that unaided humans are really terrible at monitoring boring automation. So driver monitoring is going to be essential anytime the driver assistance functions take control of the vehicle and conduct the driving task. Moving on to the other modes, in automated mode, the car drives. The vehicle drives and the vehicle handles driving safety. The driver does not need to pay attention to driving. If there's a vehicle where you say, well, the car drives itself, but the driver needs to pay attention, that's not automated. That's supervised driving. To be automated, the car completely owns driving and driving safety. As you can see in the picture, in an automated vehicle, it needs to be okay to watch a movie or read your email or do something else because the car has it. Driving problems cannot be dumped onto the driver. So in automated mode, it's not okay to say, well, the driver doesn't need to pay attention, but if something goes wrong, we're still going to blame the driver by disengaging the automation and telling driver, hey, wake up, it's all your problem, 3 seconds to impact. That's not an acceptable automated system. You have to make sure that when the car has it, the car has it. The vehicle's responsible for driving safety, pure and simple. By definition, if there's a collision with a car that's in automated driving mode, it is not the fault of the human, it's the fault of the car. There is some tension between safety and permissiveness in automated driving, and this is a key thing the industry is going to take a while to work on. The idea is that you want safety, but you also want the car to go places or else it's not a very useful car. And from a sensor point of view, what you have is a tension between false non-detections, so I'll call those false negatives, because false negatives generally hurt safety. If you fail to detect a pedestrian that's in the middle of the road, that's going to adversely affect safety. But at the same time, false detections, false positives, generally hurt permissiveness. If you're constantly seeing ghost pedestrians in the middle of the road that aren't really there, you're not going to go anywhere. You're going to keep stopping to avoid the ghost pedestrians. Typically in sensors, there's a trade-off between false positive and false negative. But in automated driving, you need exceedingly low false negative rates because you can't afford to miss an object that is important to avoid. But at the same time, if that cranks up your false positive, so you're always seeing ghosts, you're not going to get to go anywhere. And this is one of the primary challenges that's going to face automated vehicles. Yes, things like sensor fusion can address that, but the point is that it is always going to be a difficult trade-off to get right. In autonomous mode, there is no human oversight. The vehicle handles driving, the vehicle handles vehicle safety, it handles driver safety, it handles everything. So there's an empty cab, there might not even be a place for a driver if it's a delivery vehicle. That means if there are passengers or cargo, it has to monitor the safety of those passengers and cargo. It needs to be an automated captain of the ship. And it needs to handle non-driving issues. For example, if there's a crash, say the vehicle gets hit by another car, it needs to know how to handle post-crash responses, such as calling emergency services all on its own. Because the point is, there's no human to know that it was even in a crash to take care of that. The human driver or human passenger is not tasked with doing anything about safety in these vehicles. Now, that doesn't mean there's no humans involved at the bigger system level. It's okay for a vehicle to get help if it decides on its own it needs it. Just as if you're in a car crash and you call emergency services to come help you, it's okay for an autonomous vehicle to call its support staff or emergency services to get help after a crash or after something's happened. The point is, though, there's no human continuously babysitting it, waiting to see if there's a problem. The vehicle's all on its own to know something's gone wrong and then call in for help when it needs it. This adds a requirement for non-driving sensing, and UL 4600 safety standard covers automated and autonomous vehicles, but especially includes things beyond the actual driving task because human drivers do more than drive, and autonomous systems are going to have to do those same tasks. And that includes passenger safety, cargo safety, monitoring vehicle equipment status, and so on. It's important to note that things beyond the driving task are outside the scope of automated driving systems as described in the levels of J3016. Therefore, making a safe autonomous vehicle requires not only dealing with the driving system, but also these other aspects that are covered in UL 4600, but are outside the scope of the J3016 level system. Back up at a higher level, let's compare and contrast the different driver roles. In assistive and supervised driving, driver attention is required. As you can see from the yellow oval, the driver is in charge of driving safety, regardless of whether the human driver or the vehicle is conducting the actual driving task. The vehicle responds to the driver either all the time or when required to ensure safety. The vehicle gets blamed for unsafe interventions in either case, and that means there's some sort of incentive for the vehicle to sort of underperform. The vehicle gets credit. It's the hero if it prevents a crash. But if it causes a crash, that was a malfunction because the driver is the one who's supposed to be making sure of safety, and any technology that causes a crash overrode the driver and is therefore causing a problem. On the other hand, in automated and autonomous driving, the vehicle is in charge of driving safety. It's not a human driver's problem, it's the vehicle's problem. And that means the vehicle cannot count on a human happening to notice something is bad, because as soon as you do that, you're down in supervised mode. Along with this, mode changes are requests not but demands by the vehicle, and I'll go into this more in a second. But the idea is that the vehicle can't just dump a problem into a human's lap and demand it be cleaned up. Let's go into that in a little more detail. Driver mode transitions are a key aspect to getting safety. And a significant issue here is known as the mode confusion problem. In mode confusion, the automation and the human driver have a different idea of what state the system is in. That means that it's essential to have positive driver acknowledgement when going from one of the modes lower on the chart to one of the modes higher on the chart. In particular, it's essential not to demand that the human accept a role for which the human may not be ready for. It's okay to request user attention, but it's not okay to demand it and be unsafe if the demand is unfulfilled. Let's get a little more concrete. For example, say you're in a supervised vehicle and it decides to change to assistive mode. A little light comes on the dashboard, maybe there's a little tiny ding, and then all of a sudden you're in assistive mode, and that means the human now is driving. If the human is preoccupied or just not paying enough attention, they might miss the little light and the little ding. Maybe there's a lot of road noise, who knows? And the driver might think the steering is automated when in fact the driver should be steering. Now the good news here is that since the driver is still in charge of driving safety, they're supposed to notice if the car starts wandering out of its lane. But it still could be an issue if the dropout happens, for example, right before a red traffic light where the vehicle is supposed to be braking and the braking is delayed. So it's important that the driver actually understand that it's dropped out of supervised to assistive and the driver acknowledge assuming that additional responsibility. It should be no surprise if a driver who's engrossed in a movie or reading email takes a significant amount of time to re-engage with the driving task. They have to stop what they're doing, they have to look up, they have to look around, they have to figure out what's going on. That could easily take 30 seconds, it could take a minute, it could take longer depending on what their state of mind is and how complicated the situation is. It could also be that in an automated vehicle, the captain of the ship doesn't have a full driving license. At some point, if the vehicles are completely automated, what's the point of having a driver in charge? Really, all you might need is a responsible adult with some sort of lesser license or just a responsible adult. It's unreasonable to ask a human to re-engage with a complicated situation. And don't forget, if the automated system can't handle it, that probably means it's not an easy thing for the human to handle either. Finally, in autonomous mode, there may be nobody in the vehicle, or the person may be completely asleep and expecting to wake up several hours later in a different city. Think about the last time an alarm went off and you turned off the alarm and went back to sleep. That could certainly happen with a passenger in an autonomous vehicle, even if you're just degrading to automated because of some sort of problem with a vehicle. So think about, if you're designing these systems or using these systems, what it means to shift modes and how you can be sure that the human is not only asked to take an additional responsibility, but actually accepts and is capable of performing that increased responsibility when doing a mode change. There's some technical safety challenges that need to be addressed in these vehicles. For assistive, we should see more uniform adoption of safety standards such as ISO 26262. The automotive industry is the only industry I'm aware of in which there's a mature safety standard, but the companies building the product do not publicly say that they conform to the standard. As this technology becomes more highly automated, and people become more dependent on its correct operation for safety, it will become increasingly important for the industry to conform to established safety standards. For supervised automation, it's important to realize that safety credit is given if there are low false positives. So that means if 19 times out of 20, an active safety system saves the day and prevents a crash or prevents injuries, then the ADAS system is going to get the credit. The active safety wins if even only 19 times out of 20, even only 9 times out of 10, it does the right thing and saves lives. That's a victory because the driver was not supposed to make the mistake in the first place, and it's saving the driver from a mistake. It is, however, essential to have effective driver monitoring because automation complacency is a real issue, especially with the higher levels of automation involved in driving. For automated driving, in which the vehicle actually does all the driving task, not a human driver, then it's going to be increasingly challenging to do safety of the intended function, especially scenario completeness and coverage. Because at this point, if there's any gaps in things the vehicle knows how to do, it's the vehicle's problem because it's fully in charge of driving. The specific challenges here are sensor fusion, perception, and prediction. But an additional challenge for social acceptance is that, unlike supervised driving, in which any automation features get credit for saving the driver, in fully automated systems, the automated vehicle gets the blame. If it's not 100% every time it causes a crash by not being perfect, it gets the blame because there was no driver to blame and no driver responsible for the crash. It's all on the automation. And so that means for automated driving, you need not only low false positives to get good permissiveness, but for every false negative that results in a crash, the automated system gets blamed. So the emphasis isn't on getting a pretty good blue slice of the pie here. The emphasis is you get blamed even if that red slice is a little tiny sliver. If it's not better at least than a normal human driver, then that's a problem. And for autonomous, you have to do even more than just driving. You have to take full responsibility for every aspect of vehicle safety. UL 4600 goes on about this at length. But the takeaway here is drivers do more than drive, and you have to cover all those bases if you want to actually build a completely autonomous vehicle that's safe. For companies making components, there are specific safety challenges. I like to think of it as positive trust balance. You need engineering rigor, you need validation, you need feedback, you need safety culture, and you really want to have a standards-driven approach to safety. Part of this is going to be safety performance indicators. If there's a vehicle manufacturer that's buying a piece of equipment, they're going to need to know what they can expect from your component, not only in functionality, but in terms of safety, and they're going to want data for that. I expect integrators will start asking for more than conformance certificates to something like ISO 26262. They're going to want to know component safety cases. It's not going to be enough to say, well, this is a 26262 ASIL-D component. They're going to need to know what kind of situations it's designed to handle, what kind of situations it has a problem with, and what assumptions have been made about the operation of the system. For example, if you have a sensor that's great in normal hazy days, but has a problem in direct sunlight or has a problem in rain, you need to know those sorts of things, in addition to whether it's safe for its intended operational design domain. It's almost certain that as this technology matures, there are going to be lessons learned, both during development and during deployment. It will be essential to have field feedback on quantitative metrics for performance. What's working, what's not working, what are surprises, things that you thought were going to work but don't, because either you didn't understand the technology, you didn't understand the full scope of the requirements, or the world changed out from under you and things are different than you assumed they were when you designed the system. So safety performance indicators, SPIs, will be essential to feed back not only to the component developer, but to the vehicle developer so they can understand how the performance and assumptions change over the life of the equipment as they're issuing safety updates. Another challenge is scalability past pilot vehicles. Accurate perception and prediction is still a work in progress, and getting things to work pretty well for 1 car or 10 cars or even 100 cars is at a vastly different scale than getting something to work for millions of cars, where all the rare edge cases suddenly become daily events for some vehicle in the fleet. I expect that this is going to force a transition from a brute force data collection approach. As the long tail of edge cases and odd things happens, you're going to need to take a more structured approach to talking about safety. You're going to need a safety case to not only say, well, we haven't seen a problem in so many million miles, so probably it's okay. You're probably going to also need to say, and here's why you should believe that's probably true, because we've thought through it and it makes sense that we haven't seen any problems. A key point in the safety case is going to be resolving the issue of potential multi-sensor correlated failures. If you have multiple sensors that do okay, you can say, well, I have multiple sensors that do okay, so what are the chances they all fail at once? And the issue is that there are going to be common cause failures across the sensor modes, and you have to think about those, you have to reason about them, you have to account for them in your safety case. Here's an example in which a camera didn't see this man who might or might not be about to cross in front of my car in downtown Pittsburgh. A contributing factor was there were a lot of vertical edges that caused some performance problems. But if you say, okay, the camera didn't see him, the radar will, well, the radar sees the man, but it also sees the trash can, it also sees the light pole, and it's not clear if it'll be able to distinguish them, especially since the man is still standing still right now as I approach him. So there's nothing moving. It's unclear if a radar would have seen that man or not. And same issue for the LiDAR. It might think that the man and the pole and the trash can are all part of the same object. Now, every particular system will have a different approach to this. But the point is that the limit to safety is going to be having sensor fusion algorithms that are dependably diverse so that you make sure they don't all fail in the same way on the same scene. There are also some organizational safety challenges. There's significant pressure to deploy. In 2020, especially late 2020, we saw a big flurry of empty driver's seat demos of varying degrees of readiness for actual production. It's hard to believe that that flurry of demos had no relation to the end of the year and a need to report some progress by the end of 2020. And the question is, can teams take the time needed for safety? If they're under schedule pressure, will they be able to actually push back if they're not ready? Will they be able to actually get as safe as they need to be despite the realities of funding and schedules? Some industry transparency is appropriate to help the public accept that the right thing's being done for safety despite inevitable business pressure. It would help a lot if there was safety collaboration rather than competition. In the airline business, they don't compete on who crashes less often than someone else. The public expectation is all airplanes are safe, all airlines are safe, and they compete on other factors. And the car industry is going to need to get there as well for people to really trust this technology. Transparency will be required, because having the public believe you're safe because you have a really good marketing campaign is one thing. But when the inevitable adverse news event happens, if the public trust has been based on claims rather than transparency, the first crash that results in a fatality negates all the claims. And now, because there's no transparency, there's no trust. So it's essential for the industry to get to a place where the public not only believes they're safe, but does it because the industry has been very transparent about safety. So if the day comes when something bad happens, the industry has a cushion of transparency and a well of public trust so that the public understands that the technology is not perfect, but the industry's been straight with them, and so they have a reason to believe things are still okay. A base for all this is going to have to be a robust safety culture. In practice, you're not going to get safety unless you have a really good safety culture. And there are two dimensions of challenge here. The first is robotics meeting automotive engineering. Those are two different cultures, two different backgrounds, two different disciplines, and melding them together is already a cultural integration issue that's proceeding at the various companies. But underneath that is a deeper cultural reconciliation that's still in progress. There's the Silicon Valley move fast and break things culture, which can work great for consumer electronics, but is not really intended to be used on life-critical systems. There's the automotive culture, which has been building life-critical systems for a long time, but until now, they've always had a driver to task with cleaning up the loose ends, so they can reduce cost by tasking the driver with dealing with minor malfunctions. But now that there's no driver, that doesn't work anymore. So now there's no human driver. The automotive folks have to get used to dealing with there's no driver to clean up small things that in principle, even a small thing can lead to a bad crash if not mitigated. And they have to deal with integrating with a culture that is all about time to market and good enough functionality. Except we're trusting our lives to these vehicles, so they have to get it right.